Hi everyone, so today we have a very nice question involving something called as rational root theorem and quadratic polynomials. So we're going to see how we can maybe apply this RRT to quadratic polynomials. This is called RRT in short. And this question is a pretty good mix of algebra and probability. So yeah, let's just get started. This is the problem number 6 from the AIME II exam in 2018. And in this video, we're going to look at how we can find the roots of a quadratic polynomial using the rational root theorem, of course. And then obviously we have certain book sessions from National Math Olympiads, and at the end, a simulable challenging problem.
This video is sponsored by Cheenta.com. Since 2010, Cheenta has trained thousands of students from all around the world in mathematical Olympiads, physics Olympiads, computer science and informatics Olympiads, ISI CMI entrances, and research projects for school and college students.
Okay, so it says that a real number a is chosen randomly and uniformly from the interval -20 to 18. So a is a real number that belongs to this interval -20 to 18, right? It's a real number. It can be anything. It's not necessarily an integer. Now, they're telling us that the probability that the roots of the polynomial p of x are all real can be written in the form of m by n, find m plus n. So we just need to find out the probability essentially. So what do I think of when I look at this? So we have this px, right? It's a quadratic polynomial. It's not a quadratic, which is the major issue over here. Plus -4a plus 3 times x minus 2, right? So had this been a quadratic, right? And what are they asking? That roots of the polynomial are all real. So let's say we had a quadratic. Let's say we had g of x is equal to ax squared plus bx plus c. So when would the roots of this be all real? When the discriminant is greater than or equal to 0. It would be real and distinct if it was greater than 0. But since they are just talking about the case where it is real, we can have equality as well. But in other words, b square minus 4ac needs to be greater than or equal to 0. This would be the case if it was a quadratic. The problem over here is that it's a biquadratic. So what I'm going to need to do is maybe convert this biquadratic or this quadratic equation into a quadratic equation. How can I do that? Factorization or from whatever other techniques I have. So we have this p of x is power 4 plus 2ax cubed plus 2a minus 2 times x squared plus -4a plus 3 times x minus 2. So if I can maybe find out certain roots of this polynomial p of x and then maybe use long division and then just factorize it, basically reduce it down to a quadratic, my work will become very, very simple, right? Because we have the result for when the roots of a quadratic are real. There is no such standard results for quadratic, right? For a biquadratic. So that's the issue. Now, how do we find the roots of this p of x? Right, that is where the rational root theorem comes in, right? Rational root theorem, or in short we call this RRT. Okay, great. So what does this say? So let's say we have a polynomial p of x, a general polynomial. So a0 plus a1x plus a2x square all the way up to an x is power n. So this theorem essentially states that if a rational root exists, if a rational root of p of x exists, then it will be of the form p by q, right? Then it will be of the form p by q. And what is p? P is basically a factor of a0, rather the factor of the constant term, and q is basically a factor of an, the leading coefficient. So let me just give an example. So for example, we have, let's say, the polynomial x square minus 5x plus 6. Now we know that the roots are 2, 3, right? But how do we maybe apply rational root theorem over here? So rational root theorem says that if there exists a rational root, then it will be of the form factor of 6 divided by factor of 1, which is 1. And factor of 6 can be 1, 2, 3 and 6. But when you apply the rational root theorem, you consider both plus minus, right? So plus minus 1, plus minus 2, plus minus 3, plus minus 6. These may be the possible rational roots of this polynomial. And we know that 2, 3 are actually the roots. You can find that out by factorizing or using the quadratic formula. So this is effectively what the rational root theorem is telling us. So if I try to apply this rational root theorem to this polynomial p of x, I see that if a rational root exists, it needs to be of the form plus minus 2 or plus minus 1. Right? Because it's going to be both, right? It can be 1 also and it can be 6 also, the ending term as well. Right? So basically plus minus 1, plus minus 2. These are the only possible rational roots, or in this case integer roots, of our polynomial px. Right? Great. Now it so happens that x equals to 1 is a root. Why? Because when you plug in x equals to 1, let me just write this again. Px was this, right? 2ax cubed plus 2a minus 2x squared plus negative 4a plus 3x minus 2. So if I just plug in x equals to 1 over here, so at x equals to 1, I get 1 plus 2a plus 2a minus 2, negative 4a plus 3 minus 2. So 2a, 2a, 4a, this gets cancelled with this, and negative, negative, negative 4, 3 plus 1 is 4, so this becomes 0. So x equals to 1 is a root of this polynomial p of x. Now similarly, x equals to minus 2 is also root, and you can just check this out yourself, the similar idea. So basically, p of x will be x minus 1, x plus 2 times some other polynomial, let's call it q of x. And you know, it's very easy to find this q of x. You just perform long division. You know what p of x is, right? This is p of x. And then you just divide that by this quadratic, you will get q of x. And it so happens that q of x is nothing but x square plus 2a minus 1x plus 1. Right, so you just need to perform long division over here. I'll leave that to you. Now, what next? So the question says that we need to have all real roots, right? Probability that all roots are real. So we need to find under what situations are all roots real. So x equal to 1 is a real root, x equal to minus 2 is a real root. So if this polynomial p of x needs to have all real roots, q of x needs to have all real roots. So therefore, roots of this new polynomial q of x also need to be real. And this is great because q of x is a quadratic polynomial and we can deal with quadratics a lot easier. So basically discriminant needs to be greater than or equal to 0. So basically minus 4 times 1 needs to be greater than or equal to 0. I just open this up. I'll get 4a squared negative 4 and negative 3 greater than or equal to 0. I can easily factorize this by splitting the middle term into negative 6a and 2a. So this very nicely factorizes as 2a plus 1 and 2a minus 3 is greater than or equal to 0. After this, it's just a game of the wavy curve method. So to basically determine the interval in which a lies, right? So we see that a has to be less than or equal to negative 1 by 2, or a can be greater than or equal to 3 by 2, right? So if I were to write this in interval notation, a would belong to negative 20 to negative 1 by 2 union 3 by 2 to 18. Why? Because they told us the interval of a, right? They're telling us in a way the interval of a over here, right? A can be any real number between this interval. So in a way, the limits of a are kind of fixed, right? It can go up to negative 20 or it can go as high as 18. So it's like very fixed interval. We get to finite intervals over here. Okay, great. Now what's the probability that all of them are real? So if this happens, then that implies that all roots are real. So basically, if the value of a is within this interval, then all roots of the polynomial p of x will be real, right? And if it's not, then it won't be real, right? So what's the probability? Probability that basically the roots are real, that will be the length of this plus the length of this, right? So that will simply be 18 minus 3 by 2 plus negative 1 by 2 negative 20. Basically finding the distance between those two endpoints, divide by the total distance, right? So total distance was from negative 20 to 18. So I can write this 18 negative 20. Basically the distance, right, on the number line. So the probability would simply be 18 negative 3 by 2, which is 33 by 2. And this becomes 39 by 2 divided by 38. And this probability then simply comes out to be 36 divided by 38. It so happens to be 18 divided by 19 in the simplest form. And this they are told was in the form m by n. So m plus n is nothing but 18 plus 19, which is 37, and that is our answer. So yes, a very cool problem. We basically reduced down the quadratic polynomial into a quadratic polynomial, and after that it was just pretty easy to deal with. So yeah, hope you learned something from that. Okay, so moving on, we have some book suggestions for the USAMO or AIME. Elementary Number Theory by David Burton, Problem Solving Strategies by Arthur and Gell, Functional Equations by Venkatachala, Problems in Plane Geometry by Sharigan, Elementary Number Theory by Sierpinski, Graph Theory by Harari, and Combinatorics by Brualdi. Okay, sadly I have a similar but challenging problem. So let P be a number ABCD, which is also a prime number, and then I wanted to prove that the polynomial ax cubed plus bx squared plus cx plus d cannot have a rational root. It's impossible for it to have a rational root if P is a prime number, ABCD. So maybe try this out, and if you're able to solve this, let me know. Until then, I'll see you in the next video. Thank you very much and bye-bye.
The programs are designed for students who are passionate about mathematics, and they are personalized with one-on-one training, individual evaluation, and remedial sessions. The reason Cheenta students are successful over the last 10 years because they are taught by mathematicians and real Olympiads from leading universities in India, United States, and Europe. Some of our students come back to teach at Cheenta from Oxford, Cambridge, Harvard, MIT, UCLA, ISI, CMI, IITs, TIFR, and IISc. For more information, visit cheenta.com.